Hi everybody, this talk is about how Nielsen built a multi-petabyte data warehouse using Amazon EMR and Amazon S3. What if I told you you can take your third-party data warehouse and transition it to run over Amazon S3 using EMR, and it's going to run like a race car? Not only that, you're going to save a ton of money when doing this. This is exactly the situation we were in 2019. We were running a third-party data warehouse, and today we're running it all on EMR and S3. Back in 2019, our third-party data warehouse had excessive costs. It was costing us over $3 million a year, and we were getting a constant nagging from management to reduce the cost. Whatever we did was futile. We couldn't really drive the cost significantly. In addition to that, not all the raw data was accessible. Our data scientists and analysts kept asking us to write custom reports for the data that was not accessible, and this was creating a lot of friction with them. So again, not a great situation to be in. After moving to EMR and S3, our new data warehouse is saving us $1 million a year. All the data is now accessible, and the nice thing about it, it's available immediately. So this is a better solution all around. So in this talk, we're going to tell you all about it. We're going to tell you what problems actually drove us to look at this solution, what kind of solutions we explored and ended up with EMR. We'll tell you how we pushed the AWS envelope further to get really good performance. And I think you'll conclude that it's easy enough and you can build one as well if you'd like. Before we start, I want to tell you who we are. My name is Ofer Dubrovsky. I'm a big data dev lead. I love to tinker with systems and delight our customers. And with me is Yair Reuveni. Yair.
Hi everyone. I'm leading the data engineering group in the Nielsen Marketing Cloud. And my motto is, when you build a platform, never be the bottleneck.
Okay, so to give you some background about what kind of problems we need to solve and how we wanted to solve them, let me tell you about our product called Nielsen Marketing Cloud and what we do. Nielsen Marketing Cloud is a data management platform. We create marketing segments and device graphs, and then our customers can use this for running campaigns and targeting campaigns and making business decisions. Our customers are basically marketers running campaigns on the various ad networks that are partners of ours. In a nutshell, we're cloud native. We collect about 60 terabytes of new data every day. In total, we store about 5 petabytes of data, and we're heavy users of Spark. Roughly, I could say that we run about 6,000 Spark nodes a day across all our clusters. The segments I mentioned, so segments are basically lists of user IDs and device IDs that have a label. So for example, think about it kind of like a mailing list. So we have a list of all the IDs of users who love pizza or who like running and cycling and so forth. And every group has a different size. Questions that marketers love to ask are, how many pizza lovers are also into cycling, because maybe we want to run a campaign and send them a coupon for pizza. So we deal a lot with questions like intersection of groups and count distincts. And usually these are really tough problems to compute. They're very intensive for Spark. So there's a lot of data shuffle going on between the executors. So it's a tough problem to solve, especially with our data size. Our biggest table has 2 petabytes of data. So if you run a full scan on it, that creates a lot of shuffle. All right, so our journey begins. And to tell you all about it, I'm going to switch over to Yair. Yair?
Our journey begins. This is us, 2019, driving our comfortable, safe, familiar car. And we were loving it. Well, not exactly. Let me tell you why. See, our raw data was sitting on S3, and we were building marts using Spark on EMR on S3. Marts are basically transformations and projections of the raw data. Then we were loading those marts onto a third-party data warehouse, and our data scientists and analysts were using the data there. They were building their models and running analytics and research. Now, as you can obviously see from this setting, we were always the bottleneck. Why is that? Well, every time somebody required a new data set or a change to an existing table, it always came as a request to R&D and was competing for priorities. It was a constant cause for friction. Moreover, many times people only wanted those one-time small analysis to be made on the raw data itself. That also came to us. And we had to write those custom reports using Spark, which was exasperating and time-consuming. Bottleneck. I hate being a bottleneck. Another thing is cost. It's like running your car. Something breaks down every few weeks. You got to take it to the garage, and you get a shock from the bill. Same was here for us. As Ofer mentioned, this system was costing us around $3 million a year. Importing the data alone to the third party was costing us $800,000 a year, and the storage on the third party was costing us $1,200,000 a year. And same as it is with your car, when something breaks down, same goes for it here. When we had an outage, we always had a lot of rerun and reload of data that also came with additional excessive costs. Costs were just piling up, and we were always under pressure by management to bring the cost down. So we thought we had to find a better way. And we thought, what if we could remove the third-party data warehouse and find a way to give our users direct access to the data that was sitting on S3? That way, we can kill two birds in one stone. On one hand, reduce the excessive cost, and on the other hand, remove ourselves as the bottleneck. We had one more of those huge outages and very big rerun, reload, and excessive cost issue in production. I was actually losing sleep over this. And I thought, how can we solve this? We kicked off the project, set up the goals. First thing, the new solution had to provide similar capabilities as the existing one had. It had to be simple and self-serve, and also support programmatic access, since our data science were automating SQL into their code, either for ETL flows for building tables, or in utilities used to compute their models. Second, it had to support those huge data sets of a 2-3 petabyte marts, and also those large queries with heavy shuffle on them. And finally, maybe the main motivator for this project, it had to come with a lower cost. We started with a benchmark, and the first thing we checked was Athena. Athena is widely used in our organization for various analytics and dashboards. We benchmarked our data science use cases on Athena, and it worked pretty well on the small use cases and small queries, but on the mid-range queries and large queries, it failed. Also, you can't really optimize the engine itself, and it's influenced by the overall usage in the account. So we thought, maybe using Presto as the query engine is a good paradigm. We only need to optimize it better, tweak it, enhance it, configure it better, choose better hardware. We decided to go in the direction where we give each user their own cluster for resource isolation. And we benchmarked this setting. It actually worked pretty well for many of the use cases. But on the heavy queries with heavy shuffle, on those 2 petabyte full scans, it didn't work. It failed with out-of-memory issues. And even when we played with the spill-to-disk capabilities of Presto, it still wasn't good enough. Back to the drawing board. So we thought, how can we solve this? And then we realized we have been solving these same large, big problems for years now, using Spark. We benchmarked Spark SQL on our data science use cases. And amazing, it worked great for all of the use cases and queries. Actually, for some of them, it was even faster than the third-party data warehouse. The only question was, can we make Spark accessible and friendly enough for our users? We wanted a simple and clean user experience. We chose Spark over EMR and gained all of the off-the-shelf features that come with EMR. For example, easy to set up cost tagging that we later use for cost management and control. Features like Zeppelin, which we gave our users as a studio for running their SQL, or the Spark thrift server, we used to give JDBC access, to provide JDBC access. We went in the same direction where we give each user their own cluster for resource isolation. And we gave our users a selection of cluster sizes ranging between 100 cores to 2,500 cores. And the way they work with it is they play and develop their queries on the small clusters on small scale data. And when the query is ready, they can run it on the full scale in the large queries, in the large clusters. And we had to build a system to manage those clusters. We have set up a central Hive metastore and all of the required tools to get our marts and tables published and refreshed there. We decided not to invest too much in a UI for spinning up the cluster, so we chose Jenkins for that. Let's take a look at our architecture again. We still have our raw data sitting on S3, and we're still building our marts on S3. Now we have a centralized Hive metastore, and we've built a launch service to launch and manage those transient EMRs. And our users are interacting with the data either using the Zeppelin UI or through JDBC. We also now support automating flows on JDBC based on Airflow. Let's see how it works. So the user comes into the Jenkins build page, and they can choose a cluster out of a preset selection of cluster sizes. They also can get a general sense of the overall cost of the cluster they choose. And they also need to provide a cost tag that is later used for cost controls and management. Once the user hits the build, the launch service goes into action and launches the cluster. We also have a feature for terminating clusters after 45 minutes they have not been in use for better cost performance. When the cluster is up, the user gets a Slack notification with all of the information required to interact with the cluster. So if he chose a secure cluster, he gets a one-time password for that specific session and cluster. And if he chose a JDBC cluster, he gets the JDBC connection URL. And if he chose the Zeppelin cluster type, he receives a Zeppelin URL. And then all the user has to do is click the link and start to work. If the user chose the JDBC option, then all the user needs to do is to take the JDBC connection URL, plug it into his favorite JDBC client, and then just interact with the cluster, same as you would do with any other database, with SQL. As for Zeppelin, Zeppelin is an open source notebooks framework for analyzing and interacting with data. It natively integrates with Presto and Spark, and we have configured the default so that when the user comes in, all you have to do is write SQL, and it runs Spark SQL behind the scene. Of course, the user can also write Spark code in Zeppelin, like in other cases. Also, we store the notebooks on S3, and on each cluster the user spins up, all of his work is loaded, and he can continue from wherever he stopped. As for programmatic access, we have built a raindrop, an Airflow operator that our user can use to spin up JDBC clusters and automate and schedule queries to build marts and tables automatically. And our users even went a mile further, our data science went a mile further, and built their own utility that also comes with machine learning capabilities. Now, the nice thing about choosing Spark is it comes with a nice Spark UI. And even for non-technical users, it can give some insight into what's happening in the cluster, especially the SQL tab. This is an example for a simple query that somebody ran. And our users, they definitely take our system to the extreme. They run crazy workloads with super complex join logics. And we are amazed by these things they run. Look at this example. It ran for 25 minutes. Now, let's talk about results. Well, the first amazing fact about this project, it took us only 4 months to reach the first working MVP solution. It took us only 4 months of 2 engineers with a supporting team giving advice. And if you take our learnings, you maybe can do it even in less. Let's look at our system in the numbers. Since we are in production, we already have over 1,000 tables. And since users are creating tables and we have automated flows that generate tables, this number goes up every day. We have around 80,000 Spark core hours per day. And we already have over 100 cost tags, which means we actually have over 100 different projects running on this system. Let's take another look at costs and see how we done compared to the previous solution we had. We're still building the marts on S3, so that cost remains. We still have the $600,000 a year. And in the queries, we are still in the same ballpark in terms of cost. We managed to reduce the cost in the storage by optimizing the structure and a better cost on S3. And we don't have that import cost of $800,000 a year. So all in all, we saved over $1 million a year. Now, for pushing the envelope, I'll pass the mic to Ofer. Ofer?
All right, let's talk about pushing the envelope. And I want to start with costs, which are always on everybody's minds. Let's look at our instance type. We are using i3 8 extra large instances, and those cost, if you use on-demand instances, around $250 an hour. If you instead select spot instances, they're around 75 cents an hour. So that's something like 70% cost reduction. Moreover, if we look at our largest cluster, which has 80 instances in it, and a typical run of 4 hours, that would cost, using on-demand instances, $800. If we use spots, it would cost $280. So not only is it a huge reduction in percentages, it's also a huge reduction in actual cost dollars paid. So obviously, spots it is. We really want to use spots. However, when you look at the frequency of interruptions for this type of instance, it's over 20%. So that means if you select a large cluster and try to start it, you might not get the instance you need. And if it runs for a long time, there's a high likelihood of losing those spots and actually losing your whole job, which obviously is not a good idea. So our solution is twofold. On the one hand, we are using instance fleets. That's a feature of EMR that allows you to select alternative instances you're willing to work with. The more you select, the more EMR has to choose from. And you can also select multi-zones, which again further increases the amount of instances available to select from. EMR will choose the ones that are more available. So that helps in two ways. One, when you start the cluster, it's more likely you will get the instance you've asked for and get your cluster going. And second, because the more available instances were selected during that time, it's less likely that you would lose instances. So that's great. We get help here in both dimensions. The other thing we've done is we've created a spot monitor. It runs constantly as the clusters run and monitors for losing spots. If we lose the spots, it will heal the cluster by requesting to resize the cluster and get more spots. So that really solves with losing the spots problem during runs. So these two things completely solved the issue of losing spots and actually allowed us to do all our runs with spots, reducing the cost significantly. Another feature we started using is EMR managed scaling. This is a new feature that came out a few months ago and basically allows EMR to scale up or down the cluster when it's not under load. So we've started implementing this, and this really helps us, especially with our workloads. Our data scientists usually start a cluster, fire up queries as they developed on small data sets, and when they're ready, they'll run it on a larger data set. So there's a lot of low times in terms of utilization, and this really helps us solve that. In addition to that, In addition to that, we could set the idle time termination of the cluster to a longer period. If you recall, Yar mentioned that we have a feature that we set the cluster to terminate after 45 minutes of idle time. But now, because the cluster scales down to just a few instances, it's cheap enough that we don't mind leaving it on for a longer time, and that provides a better user experience for our users because their cluster is available immediately. It's just waiting for them for work. One other thing we've built is to control costs, our dashboards. Yar mentioned that we are tagging each project by each run by the project tag and the user. And so we've actually created dashboards that allow us to slice and dice by project or user and allow our users to go in and look at their costs and keep a tab on their costs. We can also detect extreme cases of costs running wild and take corrective action in time. We've also introduced low utilization alerts. So these help beyond all the previous measures I mentioned because they can happen in two ways. One, a user may select a large cluster for running really small queries on small data sets. So the cluster would be underutilized. So they would get a Slack alert telling them about that, and so they could go in and reconsider selecting a different type of cluster. The other problem is that data might be skewed, and as a result, the cluster may be working fully, but not in high load. And again, that's an issue usually with the query. So this is an indication that you might want to go into the Spark UI, take a look at the explain of the query plan, and then figure out if your query is actually could be optimized and written a bit better. Let's talk about optimizing for speed. So a great best case, best practice is to organize your data when you write it into small parts. If you can divide your data into many small files, they're called partitions, and usually these are the dimensions you query by, then Spark would be able to filter out a lot of the files it doesn't really need and not even read them. So then if you do a heavy filtering on the data, instead of doing a full scan on all the data, you might just need to read an order of magnitude less data. That has two effects. One, it speeds up the processing, which is obviously awesome. And second, it saves a lot of cost because you're not actually doing any processing on a lot of the data. The issue with that is that the data actually resides in S3 buckets. And when Spark starts, every executor will get a list of files it needs to work with, and it will do a get head to get basically a list and check that the files actually exist. As we use larger and larger clusters and need to read more and more files, we would do more of these get heads in the while starting up the query. And this could create a load on the S3 bucket. Currently, S3 buckets support 5,500 gets a second. If we take a really large cluster and send a lot of gets, we may go over this. To solve this, Amazon implemented basically a redistribution of the data. So when they detect that the load is slowly going up on a bucket, they will redistribute it to more buckets, and then you would get multiples of the 5,500 gets you can get on one bucket. However, this is really great for use cases like a website where traffic over time slowly grows, but it doesn't work for our scenario. Think about it. Our scenario is that we write a lot of data once. Every day we write more data. And then a data scientist may fire up a huge cluster and suddenly try to query all of this data at once. There's no time for learning at all. Look at this. This is our biggest table. It's just huge. It has 2 petabytes of data, and it has 2.3 million files. Let's look at our largest cluster with 2,500 cores. If we try to run a full scan on this table with 2.3 million files, you can end up with getting tens of thousands of read requests per second. And obviously, the S3 limit is 5,500. So we're going to go over that limit and get slowdown errors. that means the cluster will fail. And this is what happened to us in the beginning when we started trying to run big queries. So let me tell you a secret. So listen carefully how we solved it. We've consulted with Amazon support and came up with a way to support this. Apparently, it turns out that they can set up a static partition on our data, but needed some fixed prefix they can use because they wanted to set it up once and have it be good forever. So our solution is as follows. We added a prefix to the paths of our data, and it uses 4 digits. One is the batch ID. Batch ID, we write 4 times a day, so we have 4 digits there, 1 to 4. And the second part is the day number of the month. In total, if you do the math, we get 124 combinations, and that gives us 124 divisions of the data into 124 S3 partitions. As each one can take 500 GET requests, we get a total of 682,000 gets per second that this can support, and obviously this more than solves our problem. Moreover, this is cyclic. So we set it up once, and every month it's going to reset to the start numbers and be good again. Okay, let's talk about the future, and to do that, I'm going to switch it over back to Yair. Yair?
Okay, let's see how our system grows into the future. So one cool thing about choosing EMR is you get a lot of things off the shelf, and you also get new features and upgrades off the shelf. The EMR service team do all of the hard work of upgrading and inserting new features, and all you have to do is upgrade versions, and you gain the advantages. And in our case, since the main interface we have with the data is SQL, we don't have all of those deep dependencies to untangle, so it even makes it simpler. So, for example, we were one of the early bird adopters of EMR managed scaling. A short while of testing and integration, and we had this feature running in production, and our users started to benefit. Another example was with Spark 3. When Spark 3 came out on EMR 6, about a week and a half of upgrade and integration, and we have Spark 3 running in production. Actually, we have other areas in our group that we build Spark in, and there it's not going to be that short. It might take us months to upgrade because of the dependencies problem. Another thing we are looking into is improving our storage layer. And in the storage, we are looking to get a better performance out of this layer. So we are looking into open source solutions like Iceberg and Hoodie. Okay, let's look at some of our outstanding items. Probably one of the biggest caveats we have in our system to date is the cluster spin-up time of around 7 to 8 minutes. Probably a frustration point for our users. And we are looking into 2 approaches for solving this. The first one is keeping a warm queue of managed scaling clusters. And our user can just come in, pick up a cluster, and start to work immediately. And the second thing we're looking into is transitioning into Spark over EKS, which can also bring a solution to this. Another point that was always requested is to have source control for our notebooks. And this is something we are currently looking into integrating with Zeppelin. And for the last point, we had a long requested feature of being able to connect to external databases using JDBC. And actually, now, pretty recently, when we upgraded to Spark, we now support accessing JDBC directly from Spark and from within the solution. Okay, let's sum up. Here's what we talked about today. We showed you guys how we built a data warehouse solution based on Amazon EMR and Amazon S3. And we told you what kind of ecosystem you need to build around it and how to keep the cost controlled and managed. And we shared that probably the most important fact is to reach a clean and simple user experience. And we shared some tips and tricks on how to tune the storage, especially for those large data sets. So to conclude, you can definitely build user-facing solutions on top of EMR. And we managed to build a data warehouse that can actually give a serious fight to the off-the-shelf data warehouse solutions. and with a lower cost. And definitely, you can build it too. Thank you for listening to our session. And don't forget to rate us.